Mixtral has about 47 billion parameters. Run one token through it, and about 13 billion of them do any work. The rest sit idle. Not disabled, not pruned, and not missing, just not chosen for this token. What picks them is the smallest thing in the model. Every layer has its own router, and all 32 of them put together come to about 1 million parameters out of 47 billion. This is mixture of experts, and no, there's no math expert in here. Mixtral's own paper went looking for one. A transformer block is attention plus a feed-forward network. In a standard block, the feed-forward side holds roughly 2/3 of the parameters. A dense model can't skip any of it. Every token pays for the whole thing at every layer. Mixture of experts changes one thing. It replaces that single feed-forward network with several parallel copies, each with its own weights. Those copies are the experts. Attention, the embeddings, and the residual stream aren't touched. One copy each, shared by all 8. That's why 8 by 7b isn't 56 billion. Only the feed-forward side gets copied 8 times. Everything else is shared once, so the total lands at 47. Then it adds a router to pick between them. This video is about learned top K routing, the switch and Mixtral and DeepSeek lineage. Hash routing and expert choice routing pick differently, and they are out of scope here. Here's the router in full. One linear layer. Hidden state in, 1 score per expert out. In Mixtral, that matrix takes 4,096 numbers in and puts 8 scores out. That's about 32,000 numbers per layer, steering a 47 billion parameter model. To watch the arithmetic, I built a 4 expert layer in PyTorch. I didn't train it. I set every weight by hand, so the numbers come out clean. Every number in the next 3 scenes came out of that run. It shows the mechanism, not a measurement of any shipped model. Send the first token's hidden state into the router. It never sees the word. It sees the hidden state. The vector attention just finished mixing, which already carries the context around that token. 4 logits come out, and softmax turns them into probabilities. 0.5, 0.3, 0.15, 0.05. Top 2 selection keeps the expert scoring 0.5 and 0.3. The other 2 go dark, and dark means something specific. Those parameters don't get multiplied at all. That skipped work is the entire savings. Renormalize the 2 that survived. 0.5 divided by 0.8 is 0.625. 0.3 divided by 0.8 is 0.375. Gates that sum to 1 keep the mix an average instead of a pileup, so the layers output stays in the range a dense feedforward would have produced. Downstream, nothing can tell it was talking to 2 experts. Each expert it picked is just an ordinary feedforward network. Same architecture, different weights. Expert 0 returns 8, 0. Expert 1 returns 0, 8. The layer output is the weighted mix, 0.625 times the first plus 0.375 times the second. That lands on 5, 3. It rejoins the residual stream, the way a dense feedforward output would. No expert answered alone. Switch, Google's trillion parameter design, keeps 1 expert and scales it by the raw probability. It does not renormalize anything. Mixtral does. Same mechanism, different dial. Send a different token through the same layer. Different hidden state, different scores, the winners flip. Experts 2 and 3 light up, and the mix lands on 3, 5. That decision gets made right there. Inside that 1 layer, and nothing downstream knows it happened. Mixtral routes at all 32 layers. 1,000 token prompt triggers 32,000 independent routing decisions. Your prompt isn't assigned to an expert, it's rerouted thousands of times on the way to an answer. The router trains alongside everything else by ordinary back propagation. But you can't differentiate a top two pick. The task loss reaches the router through one path only, the gate weights multiplying the experts it chose. An expert it skipped returns nothing the router can learn from, including how wrong skipping it was. So an expert that wins tokens gets more gradient. It improves, and the router sends it even more. Shazir's 2017 sparse gating paper saw exactly this. The gate keeps converging on the same few experts, and it doesn't correct itself. The losers became dead weight you're still paying full memory for. Switch transformer adds a small auxiliary loss built on the balance score. The number of experts times the sum over experts of dispatch fraction times average router probability. That's a dot product of two distributions, scaled by the expert count. On a perfectly balanced batch, it's exactly 1. That's the minimum, and even traffic alone pins it there. However sure the router was. Pile every token onto one expert while the router's still unsure, and mine reads 2. Push that router towards certainty and it climbs to 4. The number of experts. The loss pays the router to spread the load. Some systems also give each expert a fixed capacity, and when it's full, the overflow tokens skip that expert and ride the residual stream unchanged. Never deleted, just unprocessed by the expert. Mixtral's paper went looking for the math expert across scientific papers, medical texts, and philosophy. The routing distributions came back nearly identical. The router doesn't care what the text is about. What it tracks instead is syntax and token shape. The tokens of the word self in Python often land on the same expert. Indentation tokens do too, especially at the first and last layers. Halfway down the stack, consecutive tokens repeat an expert at roughly twice chance. Some models do specialize. OL, mixture of experts, trained 64 fine-grained experts from scratch, and its routing did concentrate by domain. But that concentration is a frequency count. It's a number, not a job title. Nobody hired a math professor, and that's Mixtral's finding on Mixtral. It does not settle what every router learns. A hidden state hits a tiny matrix, softmax. Keep the top experts. Renormalize, mix, rejoin the residual stream. Repeat for every token at every mixture layer. That loop is why storage and compute stop tracking each other. Mixtral stores 47 billion parameters and runs on about 13 billion per token. DeepSeek v3 stores 671 billion and runs 37 billion, and it does not lean on an auxiliary loss to stay balanced. A per expert bias nudges the selection instead, added to the scores that pick the experts, but never to the gates that weight them. It steers the traffic without touching the answer. Memory pays for the whole giant. Compute pays only for the path. So when somebody says a model has 671 billion parameters, that is not enough information. Ask how many run per token. Ask how many experts each router picks. And ask what keeps them balanced. The real question isn't how big the model is, it's how much of it the router turns on for you.